Induced EMF and electric field. Now we have Faraday's law that says that there is an induced EMF which is minus the rate of change of a magnetic flux, and this corresponds to an induced current when we have this connected to a circuit with resistance R, so that the induced current will be induced EMF divided by the resistance. Well, why do we have a current? Because we have an induced electric field. So we can say that an electric field is induced by a changing magnetic flux, and the induced current flows in the direction of the induced electric field. For example, if we have this loop of wire, and if B changes in time, an electric field is induced in a direction tangent to the circumference of the loop. Why? Let's say that we have a magnetic field, uniform magnetic field pointing into the page, and this field is increasing in time. Then what do we need? We're going to have, according to Lenz's law, an induced current that will be flowing in the counterclockwise direction, producing a magnetic field pointing out of the page, which will be opposing this increasing flux. So this induced current is in the direction of the induced electric field. And if we look at two adjacent points on this circular wire, points A and B, and let's say that these points are approaching each other. So if we are at the same point on the wire, what should be the potential difference between these 2 points? If they are the same point, that potential difference should be approaching 0. Okay, so if the magnetic field is pointing into the page and it's increasing, the induced electric field is in the counterclockwise direction, so that the induced current is in the counterclockwise direction, creating an opposing magnetic field that is going to be pointing out of the page. Now, conservation of energy tells us that when you have a charged particle Q, which is subject to this induced EMF, Q times epsilon will be equal to Q times the induced electric field times 2 pi r. So it's going to be the closed loop integral of the induced electric field E dot ds, and we will see that this induced electric field will be equal to epsilon divided by 2 pi r, which is minus 1 over 2 pi r d phi dt, because epsilon is minus d phi b dt. What is phi b? The magnetic flux. Magnetic field times the area, which is pi r square, where r is the radius, times magnetic field. Therefore, we will see an induced electric field minus 1 over 2 pi r square dB dt, because pi r square b is the magnetic flux, and pi r's cancel, we will see it's minus r over 2 dB dt. So there is an induced electric field because dB dt is positive here. This has a minus sign. Now, if I look at the potential difference between points A and B, VAB, VA minus VB is minus the integral B to A, in the dot product of the induced electric field with the ds vector. Now, the ds vector is defined to be r d theta in theta hat direction. E induced dot ds this is going to give us basically the closed loop integral E dot ds when A and B approach each other, and that is minus d phi b dt. And E dot ds will be, this is basically going to be positive for the closed loop integral E dot ds if we follow this path. If we follow this path, it's going to be negative, so we will have to put a minus sign here to get this closed loop integral positive. So it's E dot ds when it is flowing from A to B, but it should be the same thing it will come with a minus sign if we go from B to A. So A to B and B to A will have the opposite signs. So this is minus d phi b dt. And this is telling us that since the flux into the page is increasing, VA minus VB is negative, which means A is at a lower potential. And indeed, the induced electric field points from high potential to low potential in the counterclockwise direction. But B and A and B are the same points on this conductor, which means the potential difference should be 0 volts for an electrostatic field E. Therefore, this closed path integral E dot ds equals minus d phi b dt implies that the induced electric field is non-conservative. So if I go from B to A in this manner, I obtain d phi b dt. If I go from B to A in this manner, that with zero difference, because ds will be 0 between A and B, the potential difference will be 0. So the path dependence for this closed path integral E dot ds basically tells me that the potential difference that I measure depends on which path I follow. Therefore, the induced electric field is non-conservative. So remember that for conservative forces, we should have the force derivable from a potential energy, and it should have the work done by that force independent of the path taken. Now, for the work done by the electrical force, QE induced dot ds, that depends on the path taken between A and B. Therefore, it is a non-conservative force. Therefore, the force depends on this induced electric field is non-conservative. Okay, so we have talked about induced EMF and electric field. We see that an induced EMF implies that there is an accompanying induced electric field, and the induced current flows in the direction of the induced electric field, opposing the change in the magnetic flux. In the scenario where the flux into the page is increasing, we have an induced electric field and induced current that flows counterclockwise, creating a magnetic field pointing perpendicular to the page out of the page, opposing the increasing flux into the page. If I consider two adjacent points A and B and try to find the potential difference between A and B, the induced EMF is basically telling me that it is minus d phi b dt, but at the same time, since B and A are the same points on this wire, when they approach each other, the potential difference should be 0 because ds is 0. So this potential difference calculation between A and B depends on which path I take, and therefore the electrical force Q times the induced electrical field has a work done that depends on the path taken, which implies that the electric field, induced electric field, is non-conservative.